properties. Today, our topic is periodic trends in properties. In the periodic table, as we move from left to right, or as we move from top to bottom in a group, we can see the properties are varying regularly. There is a gradual variation in the properties. So we can study these variations by taking some atomic properties as example. The first one is atomic radius. If you want to discuss atomic radius, you should know how to measure the atomic radiuses of different atoms. There are three methods for the measurement of atomic radius of different atoms. The first one is covalent radius. What is covalent radius? It is half of the distance between the nuclei of two covalently bonded atoms. For example, if you take a hydrogen molecule, two hydrogen atoms are bonded through covalent bond. If you take a half of the distance, that will be the covalent radius, half of the distance between the nuclei of hydrogen atoms, that will be the covalent radius of hydrogen atom. So one of the method to express atomic radius is covalent radius. And another one is van der Waals radius. In case of noble gases, the atoms of noble gases are individual atoms. They are not bonded through covalent bond. In such cases, there is only van der Waals force of attraction between the atoms. So van der Waals radius can be defined as half of the internuclear distance between two individual atoms, two adjacent individual atoms. That is van der Waals radius. In the case of metal, that is another case. In metals, positive metal ions are distributed in a sea of electrons. Therefore, that is a different case. So we have to approach that case differently. For that, we will use metallic radius. Metallic radius is half of the internuclear distance separating the metal cores in the metallic crystal. Half of the internuclear distance between the nuclei of metal ions, two adjacent metal ions in crystal lattice. That is metallic radius. When we compare covalent radius and van der Waals radius, we can see van der Waals radius is slightly greater than covalent radius. So what is the reason? In covalent radius, the atoms are bonded. There is overlapping between atoms. But here, there is a gap. You can see a gap between the atoms. It is van der Waals radius. So it will be slightly higher than the covalent radius. Okay. Now, what is the variation of atomic radii along a period from left to right and down the group? That is our question. Variation of atomic radius across a period. The atomic size generally decreases across a period. Atomic size or atomic radius decreases as we move from left to right in a period. What are the reasons for that? No change in number of shells in a period. For example, you consider second period. Lithium, beryllium, boron, carbon, nitrogen, oxygen, sulfur, oxygen, fluorine, and neon. So in the case of lithium, 1:2:1, two shells are present in lithium. If you take carbon, there are also two shells, 1:2:2, 2p2. Oxygen, 1:2:2, 2p4, only two shells. Fluorine, 1:2:2, 2p5, only two shells. Neon, 1:2:2, 2p6, only two shells. There is no change in number of shells in a period. If we consider all the elements in a period, the number of shells are same. Effective nuclear charge increases from left to right in a period. What is meant by effective nuclear charge? Effective nuclear charge is the nuclear charge felt by the outermost electron. The nuclear charge felt by the outermost electron, that is effective nuclear charge. So as we move from left to right in a period, the positive charge in the nucleus is increasing. Lithium it is +3, beryllium it is +4, boron it is +5, carbon it is +6. In that way, the nuclear charge is increasing. So the attraction towards the outermost electron, that means electron in the second orbit will increase. That means the nuclear charge felt by the outermost electron increases as we move from left to right. That is known as effective nuclear charge. So effective nuclear charge increases from left to right in a period. These are the reasons. And what is the variation? Down the group. You know, as we move down the group, what happens? The number of shells increases. If there is an increase in number of shells, surely the atomic size or atomic radius will increase. So we can say the atomic radius increases regularly down the group with increase in atomic number. If we consider lithium 1:2s1, sodium 1:2s2, 2p6, 3s1. So 2s1, 3s1. In lithium only 2 shells, sodium 3 shells, potassium 4s1, 4 shells. So as we move down the group, number of shells increases. And the second reason for the increase in atomic size, effective nuclear charge decreases down the group. We know at the nucleus, there is an increase in positive charge. But at the same time, the number of shells increases. The electrons are moving away from the nucleus. And as the distance between the nuclei and the electron increases, the attractive force will decrease. One of the reasons. Again, in the inner shells, there are electrons. They can shield the nuclear charge. Therefore, the nuclear charge felt by the outermost electron will be less as the number of shells increases. So that is the second reason. So what are the reasons? Down the group, number of shells increases and effective nuclear charge decreases down the group. These are the two reasons for increase in atomic size as we move down the group. Now we can see the graphs. What is the graph shown here? The first one, atomic radius plot against atomic number. Here the graph, the elements given are lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. You know, these are the elements of the second period. So it shows variation of atomic radius with atomic number across the second period. So as we move down the group, what is the variation of atomic radius? That is explained in this graph. It is increasing down the group. Atomic radius is increasing. You can see lithium. Beryllium is bigger than lithium. Boron is bigger than beryllium. Carbon is bigger than boron. Nitrogen is bigger than carbon. Oxygen is bigger than nitrogen. Fluorine is bigger than oxygen. Sorry, the opposite, not bigger, smaller. Lithium is the biggest one, then beryllium smaller than lithium, boron smaller than beryllium, carbon smaller than boron, nitrogen smaller than carbon, oxygen smaller than nitrogen, fluorine smaller than oxygen. Here it is atomic radius. So atomic radius decreases as we move from lithium to fluorine. Here the size is very small. So when you see such a graph, you should not to interpret the graph. And you have to say, it shows the variation of atomic radius along a period. And in this graph, it is of second period. And the second point, as we move from left to right in a period, the atomic radius decreases. So these 2 points you can collect from this graph. Now you see the second graph. Here also atomic radius is plotted against atomic number. But the graph shows lithium, sodium, potassium, rubidium, cesium. It is a case of alkali metals. Along a group, variation of atomic radius along a group. You can see it is increasing as we move from lithium to cesium. Or we can say the atomic radius increases down the group. Here fluorine, chlorine, bromine, iodine, halogens, group 17. In this case also you can see atomic radius increases as we move down the group. So here also you will get 2 points. What are the 2 points? This graph shows variation of atomic radius with atomic number for alkali metals and halogens. And the second one, As we move down the group, the atomic radius increases. Now, ionic radii. Ionic radius. You know where during chemical reactions, atoms, sometimes it may lose electron to become a positive ion, cation, or sometimes it may gain electron to become a negative ion, anion. So formation of cation and formation of anion always possible. In such cases, we cannot call it as atomic radius. We have to call it as ionic radius. That means the distance between the nuclei and outermost electron of an ion. That is ionic radius. And here, when we discuss the ionic radius, we have to consider isoelectronic species. What is meant by isoelectronic species? Isoelectronic species are atoms, ions, or compounds which contain same number of electrons. Atoms, ions, or molecules which contain same number of electrons. They are known as isoelectronic species. So in the case of isoelectronic species, you know, cations, positively charged ions, they have excess nuclear charge. That means more number of positive charge than that of electron. More number of positive charge. So the attraction towards the outermost electron will be high. We can expect a considerable reduction in the ionic radius of cation. But in the case of anion, what is the problem? Already it has a certain number of electrons, and it is getting, or it is accepting one more electron or two more electrons. At that time, what happens? Electron repulsion, therefore a slight increase in atomic radius. So when we compare the radii of isoelectronic species, we can say atomic radii of positive ions are less than that of negative ions. Or in other way, we can say the cation with the greater positive charge will have a smaller radius because of the greater attraction of the electrons to the nucleus. Anion with the greater negative charge will have the larger radius because of the repulsion between the electrons. Now, isoelectronic species, for isoelectronic species, examples, O2 negative, F minus, Na plus, Mg2 plus. All these contains 10 electrons. O2 minus, oxygen has 8 electrons. 2 minus means 2 excess electrons are added to oxygen. So 8 plus 2, 10 electrons. F minus, fluorine has 9 electrons. Minus means one more electron is given to fluorine. So 9 plus 1, 10. Na plus, sodium has 11 electrons. But here one positive charge is there. That means one of the electron is removed from sodium. So 11 minus 1 equal to 10. Mg2 plus, magnesium, there are 12 electrons. But here two positive charge means 2 electrons are removed from magnesium. So it will be 12 minus 2 equal to 10. All this contains same number of electrons. So these are examples for isoelectronic species. Here we have a question. Which of the following species will have the largest and the smallest size? Here, the positive ions are smaller than neutral atoms. So here Mg2 plus and Al3 plus are positive ions. Mg2 plus and Al3 plus are smaller than the neutral atoms magnesium and aluminum. And as the positive charge increases, the size decreases. So when we compare Mg2 plus and Al3 plus, which is smaller in size, Al3 plus. So the smallest ion is Al3 plus. So comparatively, neutral atoms are bigger. When we compare magnesium and aluminum, which is bigger in size, magnesium left to aluminum, so magnesium is bigger in size. So largest one is magnesium and the smallest one is Al3 plus. The next one is ionization enthalpy. What is ionization enthalpy? The definition is very important. It is the energy required to remove the most loosely bound electron from an isolated gaseous atom in its ground state. Energy required to remove at a constant pressure condition, or we can consider it as the enthalpy change accompanied by the removal of most loosely bound electron from an isolated gaseous atom in its ground state. So there are certain conditions. The removal of electron from an isolated, separated atom, gaseous atom. That atom should be in gaseous state. We are not considering solid atoms or liquid atoms, atoms in solid state or liquid state. Gaseous atom, isolated gaseous atom in its ground state, and the atom should be in its ground state. So these are the conditions. We need that conditions. So the definition is very, very important. You have to mention all these conditions in the definition. So what is ionization enthalpy? It is the energy required to remove the most loosely bound electron from an isolated gaseous atom in its ground state. Energy required to remove the first electron is known as first ionization enthalpy. If you want to remove another electron from such a positive ion, it is known as second ionization enthalpy. If you want to remove a third electron from such a cation of 2 positive charge, we will call it as third ionization enthalpy. Here we have a graph in which ionization enthalpy is plotted against atomic number. Here ionization enthalpies of second period elements are plotted. Lithium to neon. You can see as we move from lithium to neon, there is a gradual increase in ionization enthalpy. From left to right in a period, there is a gradual increase in ionization enthalpy. But if you observe this graph clearly, you can identify 2 anomalous variations in this graph. Lithium to beryllium, there is an increase, but beryllium to boron, there is a decrease. That is unexpected. We are not expecting such a variation. Again, boron to carbon, it is increasing. Carbon to nitrogen, it is increasing. After nitrogen to oxygen, there is a decrease in ionization enthalpy. That is also unexpected. If these variations are unexpected, we have to find out the reason for that unexpected variations. And we can see. Now, what is the variation of ionization enthalpy? That is our next question. Already we mentioned the first ionization enthalpy is the enthalpy change accompanied by the removal of most loosely bound electron. One most loosely bound electron from an isolated gaseous atom. As a result, we will get a positive ion. If you want to remove another electron from this positive ion, then the enthalpy change is known as second ionization enthalpy. Energy is always required to remove the electron from an atom, and hence ionization enthalpies are always positive. We have to supply energy to the system. Therefore, ionization enthalpies are always positive. The second ionization enthalpy will be higher than the first ionization enthalpy. Why? Because in the first case, removal of electron from a neutral atom, but in the second case, removal of electron from a positive ion. We have to overcome the larger attractive force from this positive ion. So the second ionization enthalpy will be more. The graphs, we can see the graphs again. Already we discussed the first one, and now the second one. Here ionization enthalpies are plotted against atomic number, but here the elements are lithium, sodium, potassium, rubidium, cesium. All belongs to alkali group or first group. So as we move down the group, what is happening to ionization enthalpy? Ionization enthalpy is decreasing as we move down the group. But here ionization enthalpy increases as we move from left to right in a period. Here ionization enthalpy decreases down the group. So along a period, what is happening? Ionization enthalpy increases from left to right in a period. What are the reasons? Decrease in atomic radius, move from left to right, atomic radius decreases. Increase in effective nuclear charge, already we mentioned it. And another cause is electronic configuration. Electronic configuration has a role. We know completely filled or half-filled configuration have an extra stability. Completely filled and half-filled configurations have an extra stability. So the electronic configuration is very important. It is difficult to remove electron from a stable species. So electronic configuration also has a role. And what is the variation down the group? Ionization enthalpy decreases down the group. What are the reasons? Increase in atomic radius as we move down the group. Decrease in effective nuclear charge. And the third one, screening effect of inner electrons. Inner electrons will shield the nuclear charge. That will shield the nuclear charge. We can call it as the screening effect of inner electrons. These are the reasons for this variation. Anomalous changes, as we already mentioned. The first ionization enthalpy of boron is slightly less than that of beryllium. Actually, we are expecting the opposite. So we move from left to right, what happens? Ionization enthalpy increases. But beryllium to boron, what is happening? The ionization enthalpy decreases as we move from beryllium to boron. Boron atom number 5 and beryllium atom number 4. What is the reason? If you want to find out the reason, first you have to write down the electronic configuration of beryllium and boron. What is the electronic configuration of beryllium? 1s2, 2s2. What is the electronic configuration of boron? 1s2, 2s2, 2p1. And you know the configuration of beryllium is a completely filled configuration. What is the capacity of s orbital? 2. It can accommodate a maximum of 2 electrons. So as a result, it is a completely filled configuration. But in the case of boron 2p1, what is the capacity of p6? It has only 1 electron, so it is unstable as compared to beryllium. So here, it is easy to remove an electron from boron as compared to that of beryllium. So when we consider the same principal corner level, an s electron is attracted to the nucleus more than a p electron. In beryllium, the electron removed during the ionization is an s electron, whereas the electron removed during ionization of boron is a p electron. That is another reason. So here we can identify 2 reasons. S electrons are very close to the nucleus, so removal of s electron is more difficult than removal of p electron. One. The second one, 1s2, 2s2 is a stable configuration. 1s2, 2s2, 2p1 is not stable as compared to 1s2, 2s2 configuration of beryllium. Now we observed another such variation in the case of nitrogen and oxygen. First ionization enthalpy of nitrogen is greater than that of oxygen. What is the reason for that? Again, we have to consider the electronic configuration. Nitrogen 1s2, 2s2, 2p3. Oxygen 1s2, 2s2, 2p4. 2p3 is the exactly half-filled configuration. The capacity of p orbital 6 and 3 is exactly half. So it will get an extra stability. But in oxygen 1s2, 2s2, 2p4, it is not completely filled, it is not half-filled. So here nitrogen has more stable half-filled configuration 2p3, but oxygen has less stable configuration 2p4. So more energy is required to remove an electron from nitrogen. Another usual question is, first ionization enthalpy of sodium is less than that of magnesium, but second ionization enthalpy of sodium is greater than that of magnesium. Account for it. So first ionization means to remove an electron from sodium. What is the electronic configuration of sodium? 1s2, 2s2, 3s1. If it can remove the outermost electron, it will get a noble gas configuration. So the removal of electron is very easy. Not much energy is not required to remove the outermost electron. But in the case of magnesium, 1s2, 2s2, 2p6, 3s2, that is a stable configuration, 3s2. If you want to remove an electron from this 3s2, large quantity of energy is required. So first ionization enthalpy of magnesium is greater than that of sodium. When we consider the second ionization enthalpy, instead of sodium, what do we have to consider? Na plus. Na plus, what is the configuration? Noble gas configuration, 1s2, 2s2, 2p6. Highly stable configuration. It is very, very difficult to remove an electron from such a stable configuration. But in the case of Mg plus, what is the configuration? 1s2, 2s2, 2p6, 3s1. It is very easy to remove that one electron from magnesium. So the second ionization enthalpy of sodium is greater than that of magnesium. Another question, the first ionization enthalpy values of third period elements, sodium, magnesium, and aluminium are respectively 496, 737 and 786 kilojoule per mole. Predict whether the first ionization enthalpy value of aluminium will be more close to 575 or 760 kilojoule per mole. What is the question? Here what is given? First ionization enthalpy values of sodium, magnesium, and I think it is not aluminium. Predict whether the first ionization enthalpy value of aluminium will be more close to 575 or 760 kilojoule. Justify your answer. We know aluminum is below boron. Magnesium is below beryllium. That means magnesium has a filled configuration. So we can say it will be more close to 575 kilojoule per mole. The value for aluminium should be lower than that of magnesium. The value of aluminium should be lower than that of magnesium because of the half-filled configuration. Another reason, because of effective shielding of 3p electron from the nucleus by 3s electrons. 3p electrons are shielded by 3s electrons. But in the case of magnesium, there is no 3p electrons. Only 3s electrons are present. Okay, I think today we can stop here. Write down the notes and try to study it very well.